This video will cover the historical and societal influences of civil structures and go through the historical bridge designs and their progression and materials used. So this covers the part of the engineering syllabus about the nature and range of work of engineers, the historical developments, and the effect of engineering innovations on people's lives, which is the environmental and societal impacts. So one of the earliest forms of bridges is the arch bridge, which was used from 2000 BC onwards. The earliest forms are found in stone arch bridges. So you see them a lot in ancient Rome. You have a bunch of stones that are laid out like this, and they form an arch shape, and in the middle you have a keystone. The main thing to note with arch bridges is the keystone is what causes the bridge to be perpetually in compression. So that's what gives the bridge its shape. You put the keystone in last, it provides outward force to the rest of the bridge and forces the rest of the bridge to remain in tension. Stone was a popular choice for these bridges as it was abundant, easy to use and easy to form. And because stone is good in compression but not in good in tension, it worked in these bridge types because they're always in compression. Nowadays, you still see arch bridges. Usually they're metal, such as steel, as they have more strength and can resist some tensional loads. The stone arch bridges couldn't span very far distances, but the metal ones, in comparison, can. Suspension bridges. So suspension bridges are characterised by their cables, which are used to support the weight of the deck. So the cables help to distribute the weight force of the deck. So if we have the deck, it's got a weight force which is quite substantial, especially when you load it. And if you just have the weight being supported by the pillars, so if it's only being supported here, and that causes a significant moment force at these points. So this force here is being multiplied by a long distance to get to these pillars, which is why you have these support beams, the support cables, because it helps to distribute that load in between both of these posts to make the moment force less. Suspension bridges were first used in India as the first known use in 1412 AD, and they were made out of rope, so out of vines, and nowadays they are used to span large distances. Suspension bridges can cover the largest spans, and they are often made out of steel, and the cables are primarily made up of smaller steel cables woven together. So a traditional cable in the suspension bridge might look like this on the outside, so if you're taking a cross section, but inside it might have 9 individual little cables inside there, and all these cables combined will be intertwined to help give it more strength. Cantilever bridges. So all a cantilever is a bridge where a section is unsupported. Cantilever bridges are characterised, usually they have a section like this where it does not have a support. So the purpose of this is to enable high clearances. So if you have a boat with a mast there, it's going to be able to get under this bridge because this bit is unsupported. Also, this allows for the potential of drawbridges. So drawbridges usually use a cantilever design. So they'll have one component with a support there and another component with a support here, but no support in the middle. And what that allows it to do, since these two are not fully connected, they're technically independent, is it means that one side can come upwards and allow for the passage of boats. So these were first used in Germany around 1867 for the modern design of cantilever bridges. Of course, you have the medieval examples of drawbridges, so the concept has been around for quite a long time. Cable stay bridges. So these work under a similar operating principle to suspension bridges in that they use multiple cables to help support the weight of the deck. Although, unlike suspension bridges, which have the cables in kind of a shape like this, connected to the deck between two pillars, all the cables on cable stayed bridges span from the supporting posts. So as you can see in this diagram, they all connect to a supporting post and span outwards from there. The beauty of cable stay bridges is the design makes them relatively quick to construct, but since they are all acting from that central beam, there is still less load force that they can withstand, so they are not able to withstand as great spans as suspension bridges, but they are cheaper and easier to construct. Composite bridges. So composite bridges essentially are any bridge that use two or more materials with significantly different properties to provide an advantage to the bridge. So the most common example of this will be your concrete bridges. So concrete bridges will use concrete and steel. So concrete is super strong in compression, so it's there to give the compressional strength, and steel is strong in tension. So as you can see in the image of this bridge here, what you have is you've got a concrete deck. So it's made out of concrete sections there, because that's going to be in compression. And usually you'll see little gaps along here which will indicate that it is precast concrete, which means the concrete is made in a factory, then brought in later on trucks, which increases the production speed and reduces costs. And then usually you'll have underneath steel girders to provide that tensional strength that you need. You can also see here that the piers are made out of concrete because they're always going to be in compression, and concrete is also able to be submerged in water and set in water, unlike steel, which will be prone to corrosion and rust in water. So the main benefit of composite bridges is that you have the multiplication, the properties of the two bridges combining to give more strength. Orthopedic deck plates. So this isn't a type of bridge, but it's a design that many modern bridges tend to use. So basically that's just when you have like a corrugated design of the deck. So if you're taking a cross section of the deck, you might have steel girders, seen in this image here, underneath, that kind of have this ridge-like shape. And this is beneficial as it helps to take majority of the mass away from the neutral axis, which is what we'll see in the next image. The further away the majority of mass is from the neutral axis, the greater the strength will be. So by using orthopedic deck plates, often made out of carbon steels, you can increase the strength of the bridge while not significantly increasing the amount of materials used or the weight of the bridge. So beam design, as mentioned before, a bridge will be strongest when the majority of mass is the greatest distance from the neutral axis. So the neutral axis is the line that's usually around the middle of the beam, and it's the point where a beam is neither in compression or tension when it is loaded. So as you can see in this top diagram, when a beam is loaded, it will tend to bend. And when it bends, the top side will be forced into compression because it's going to get smaller there, and the bottom side is being forced into tension because it's getting pulled outwards like that. And because those two are opposite to each other, somewhere in the middle, you must have a point where it is neither in compression or tension, and that's known as the neutral axis. The greater the distance of the majority of mass of the object from the neutral axis, the stiffer the object will tend to be. So as you can see in the bottom diagrams, the most common designs for members within bridges is the I-beam or box beam design, because it enables majority of the material to be the furthest distance from the neutral axis, increasing stiffness while reducing material weight and costs. Environmental impacts of civil structures include the costs of pollution for materials. Some materials tend to be toxic, such as you have in the past. They used to use lead in some of the building materials, which would contaminate the soil. Also, modern bridges that are galvanized, so zinc-coated steel, the zinc tends to contaminate the soil and can disturb the balances within that, which can impact the growth of native flora and fauna. And also, bridges use lots of resources which have to be extracted from somewhere. Usually they're mined from the ground, and that's not very great for the environment. Benefits of bridges are that they enable waterways to be bypassed. So whereas conventionally a boat would be needed to take items from one side of a river to the other, bridges allow for that to be crossed over. So the boats aren't directly polluting the water as much, as there's no fuel loss into the water. It also helps to protect the wildlife within the water, as they're no longer being impacted by these boats going frequently through. And also, when bridges are made, often abutments are formed. So abutments are the bit on the edge of the bridge. So you might see them, they might look something like this if you've got an arch bridge. These are the abutments, and usually they're put there and they help to reinforce those water banks, which helps to prevent erosion. And also, these bridges can provide passage for animals. So say if there's a lack of resources on one side of a river, the animals can cross over to the other and be able to find more food and survive. Social impacts. You've got the obvious costs of bridges, that it enables communities to become more connected. So whereas you used to have to walk a long distance to get around a river, with bridges you can just drive straight across it, which means that areas that might have been more remote become urbanised, which can lead to a loss of culture and environmental significance. So say trees might be cut down, things like that. It also means that small towns may be bypassed as the route is more direct. Also, for the people living in the place where the bridge is built, they might be taxed more heavily to cover the cost of the bridge. And also, there is a risk to the workers who work on the bridge more significantly in the past, such as in the Harbour Bridge, where a lot of the workers were put in significant danger when they were creating these civil structures. Benefits to society, particularly of bridges, is that it enables more efficient travel, because it's a more direct route. Job opportunities, you've got to have somebody maintaining those bridges and somebody designing them. Safer travel, as it's often safer to go above the water than through the water, since you don't have to deal with tides or storms. And it also helps to reduce congestion, as you don't have the time delay that it takes to get across bridges. A good example of the reducing congestion is in New York, when they built the Brooklyn Bridge. That significantly reduced the time it took workers to get into the city to do that work, which enabled much of the lower class to have more resources and do more work, and took a lot of boats out of the waterway, so it became less congested, and those boats which needed to pass through the waterway were able to do so with greater efficiency. So construction processes and materials have evolved over time. A basic overview of kind of the things that have changed are from the 18th to 19th century. Majority of bridges were made out of wood, and they used cutting techniques to join these wooden things. They might have also used wrought iron, and this wrought iron would have been made on the similar principles as wood joining. So you would have had holes and slots and pins that would join the iron together. Also in the 18th to 19th century, caissons were invented. So caissons are chambers that you submerge under the water, and through that you're able to set concrete and dig into the base of the river to create a stable foundation for the piers of the bridges, which enables those greater spans to be made, since you can have more supporting structures, not just on the banks, but actually directly underneath the bridge deck. 18th to 19th century also had lots of riveting and cofferdams. So cofferdams, that's basically just a way of blocking off water for a temporary amount of time, so that you can work on the base of the riverbed to secure the foundation of the bridge as you're building it. So modern processes, you have new methods of erecting bridge components. So a lot of that involves actually prefabricating parts of the bridge off-site, such as the casting of concrete for concrete bridges beforehand, and then bringing them into the location to build, which means that modern bridges can be built significantly quicker. You also have GPS surveying of the bridges, so as the bridge is being built, you don't need somebody to take lots of measurements and calculations. With large spans of the bridge, you can use a drone or something similar to get an aerial view of the bridge and thereby determine whether it's going in the right direction, whether it's online, whether it is equal in all axes. You also have the use of NDTs, which are non-destructive tests, which we'll explore in a later video. And those basically now allow for the testing of materials without the destruction of the bridge. Changes in materials. So in the 18th to 19th century, you mainly have iron and steels, and you have wood being used, as those are most abundant at the time. Whereas more modern bridges tend to use more concretes, which are reinforced with different things. You have pedestrian bridges, which actually use polymers in conjunction with concrete. You've also got more sophisticated steel alloys, which are refined in different processes to give the best output. You've also got your synthetic composites, so things like carbon fibre can be used in bridges if you need a super lightweight, strong bridge. And future developments may include more advanced composites, which will allow for greater spans of bridges and less corrosion, which will reduce the amount of maintenance needed. And then this brings us to the role of the engineer and these areas. So the role of a civil engineer would be, you need some people who are going to manage the oversight of construction workers and design of the bridge. You're going to need engineers working on the maintenance of the bridge, and then you're going to need some working on the materials development and construction and the actual design processes going into designing and creating bridges. So that concludes this video, and the next video we'll be looking at further components of the civil structures syllabus.